Thank you, everyone. I'd like to thank 1010 Data as well for hosting this. The Meetup last month was fantastic as well. I'd like to thank James, a colleague, for his presentation, and KX for the fantastic job they've done hosting these meetups and the pizza. Today I'm going to talk about query routing, my paper that was published just last week. So I can't blame you if you haven't had a chance to read it yet. Within this, what we're trying to do is design a KDB framework that's scalable and load balanced at the same time. So, throughout this, I'd like to break it up into different points. Common design principles for KDB plus gateways. So, really, how do we get to the point where the end products are end framework? Well, what decisions do we have to make to get there? The framework components themselves, gateway query tracking to begin with, and connectivity management plan. All important factors in a system that you expect to grow. So, within common design principles for the KDB gateways, you've got to ask yourself a couple of different questions. You can't just jump straight in and build a fantastically complex system that has 2 users. So, within our first question is, what's our end product? How many users are going to be doing this, accessing the system? What are our clients? Do we expect that to grow over time, or is it going to be a certain cap on it? Next, we got to ask, what are the number of services and sites that we're going to offer to people? That's all teams, all projects generally grow the quantity of databases that they have, the services that we offer to different people. And next we talk about the, well, you got to think, what kind of data aggregation do we need? That's a really key point. So if you're wanting to aggregate data, then you should keep it as close to the source of the data as possible. And that's important in designing your framework. And then finally, the level of redundancies and failover. If you are just working on a KDB system that you and your colleague are the only ones going to access, then potentially a server crashing isn't the biggest deal in the world. You just restart it and start over. If no one's accessing it, or you're just going to it once or twice a day, then it doesn't matter. But for a lot of production systems, it's really important that you have some sort of method for rewriting queries to a site B, or if you had a hot system that you wanted to take advantage of. Your framework should really be able to adjust to all of these different kinds of factors. So, we look at the most basic type of framework design for a gateway system. Before I go further, I'd like to explain what I mean by a service. Now, a service can be anything. Most commonly in this situation, it's going to be a historical database, just saved on a disk. It could be a real-time database as well. It could be a service that you're providing APIs for users. Anything. The service is a very loose terminology for something that needs to be executed on a queue process. Next, we've got our gateway, and this is as simple as it gets if you're going with the gateway framework. Your gateway connects to all available services, and the client interacts with the gateway and gets what they need. The pros for this kind of design is that it's very simple. Anyone can come in and take over. There shouldn't be too much code involved whenever you're building something like this. So it helps support the system. You can hand it over to someone else, you can explain it, you can write knowledge articles. It's also got a reduced IPC hop. Now whenever I mean IPC hop, I'm talking about how many queue processes is it getting to before it gets to the client. The longer it has to travel, the worse the performance of your system is. The cons of this is that there's no load balancing whatsoever. The gateway is directly connected to all of the services, and if another gateway was also connecting to these services, there's no priority given to anybody. There's no reallocation of queries. It's a very simple service that we're offering in this framework. And also, no service discovery. The gateway needs to be responsive to users. And whenever it's doing that, the gateway can constantly be looking around trying to see if there's new services available, continuously trying to reconnect or manage all of this kind of thing. So, but in a lot of cases, maybe that's all you need. Well, let's make it a little bit more complicated. Now in this, we've added a load balancer. The complexity of our system has increased a little bit, and the interaction with the client to the gateway will involve a pass-through of the load balancer. And that's the biggest con of the system. But the pros are that we've reduced the amount that the gateway has to using the connectivity management. It's just connected to the load balancer, which is connected to multiple services. This is a load balance system, so any of the queries that are coming in get reallocated to different services. And there's already a script available on code.kx with its Q-God-like quality writing of only 4 lines. So that's already available for people, and in mserve.q it will start up the required services. Spin off new queue processes that will connect to, and then pass through any queries to the next available or the less busy service that's there. Now this isn't potentially the best solution. Well, if we focus in on what mserve.q does, as I said, 4 lines of code, not too complicated. But you're not necessarily guaranteed that you're going to get your query executed in the correct order. You may be stuck behind a number of different queries for HTTP or something like that, and they're long-running queries, and it takes ages for you to get your results back. Now, this is a lot more closer to what I designed in my white paper. We've got a gateway, we've got all of the same components as the last slide. However, what we've done is we've reduced the IPC hop. So now queries go from the gateway to the service, gets executed, back to the gateway, and then to the client. The additional aspect here is the load balancer. The gateway will ask for a service. It will be allocated a particular service that it has to go to. You can see from the numbers on this that's the direction of travel that's executed. The client requesting something from the gateway to the gateway requesting a service from the load balancer, gateway being told which service is available, and then sending its queries to that service. The con of this is that if, once again, you have no need for a complex system, then you shouldn't do it. However, when you want a scalable system, whenever you're intending on your project to flourish and actually be successful and fantastic, then you need something with a little bit more complexity. Additional connection management required from the gateway. What I mean by that is, as you can see, the gateway is no longer only connected to the load balancer. The gateway is connected to both of the services in this diagram that it needs. As I said, this is the framework design that I've followed in my white paper. Now, the one difference that I've changed about it is the components are still in the right place. Whenever a service has executed a query, the service lets the load balancer know that it's now available. That allows the load balancer to immediately provide that service to another gateway, another user. So as I discussed, we have our service on the bottom, the right-hand corner. It can be anything. The gateway itself is going to be our user access interface to our framework. And it's also going to track the queries. So anything that's coming in will be tagged with a unique sequence number, so that throughout the entire system framework, we can revert back to that sequence number and find what user did it. We can find out what time the query was first sent to the gateway, how long it took, and the actual handle to the user. Where do we pass back the results to the user? The load balancer is going to be a little bit more complicated than what the mserve.q offers. It's going to provide services, so it's going to maintain the list of the table of all the available services within our plant. It's going to allocate the services whenever it's been requested from the gateways, and it's also going to act as a connectivity manager. So it'll tell all of the gateways of any new services that's available within the plant, and allocate new services to the next person in the queue. Right, there's a lot going on here. Don't worry if you can't see it. This isn't my white paper, so if you want to go and have a look. This is a diagram to try to explain how a user interacts with the system and the logical patterns that are happening whenever it's submitted. First of all, the user is going to send a query to the gateway. That query has to be very quickly validated. Is the user asking for a service that we have? If it's not, just Just tell the user that we don't have it. If it is a valid query, then we're going to request a service from the load balancer. So the query goes down here. Now the load balancer is asked, is there a resource free? Now a resource there could be multiple resources for a particular service. You could have the same HDB looking at the disk directory, but different instances of that HDB, different resources distributed on different servers. So it's all dealing with the same data, it's providing the same service, but it's an extra resource. So, is it free? Well, yes, this one's free. You're allocated to it. The gateway says, oh great, thank you very much, and sends the query onto the service. It grabs the query from the maintained query table. The load balancer doesn't see the query, it doesn't know what the query is, it just needs to know what service is required. That is then sent to the service, which is where it's executed, and it's returned back through the gateway to the user. The service, on completion of the query, will let the load balancer know, I'm now a free resource, anyone can use me. And the load balancer will check if, do we have some gateway, do we have some user waiting for this service? If it does, it will be in a service queue, then we'll allocate that user to that service. Otherwise, great, okay, we've got a resource free for the next person that comes along. User interaction with the gateway uses deferred synchronous messaging. For anyone that's not aware, that's the mixture of using an asynchronous message, using your neg of your handle, and then locking the handle for an expected incoming message back from a process. My framework does a little bit of an adaptation on that. We set up the handle, we open the connection, and then the user can fire the service that they require and the query that they want to be executed. For the paper, I wanted to simplify the logic as much as possible. I wanted to drill down into the concept of query routing, and that's why we use explicit functions. That's why we're executing user query function instead of, like for example, mserve that uses event handlers to handle incoming messages from asynchronous communication. So, user sends a query through. Now to track the query, as I mentioned, the gateway will store all of that data in a table, let's call it a query table. It's a key table based on the sequence number that's been allocated to that user. So the sequence number is unique. It's the key, and we can select any of the data from the query table by giving it that sequence number. So for example, I give it the sequence number 3, which I pre-prepared, and we're able to see that UH is the user's handle, the received time from the gateway, the sent time whenever we sent it to the service that we needed, and the return time whenever we got the answer and sent it back to the user, whether it was an error or whether it was an executed query successfully. We've also saved the user themselves, and we've saved the service handle, which was provided to us by the load balancer, the service that was requested, and the query that was executed on it. There are other fields that you can capture. You can feel free to capture the query status if you want. You could calculate the resolution time based off the received time and the return time. You could then have a grasp of the performance of your system overall and see what's actually taking a lot of time, and then maybe investigate. Find out why this service is taking so long to respond. You can also see all of the queries that have entered your system. What users are querying it the most. Are people throwing in ridiculous queries, like a select statement will provide a date partition for a massive date partition HDB. This is all available to you then. For the purpose of the white paper, we stored it in a table as well. But there are a lot of different ways that you can do this. I just wanted to show a framework design, an example of methods that you could do this with. You could store it in dictionary format or anything like that. So this is an example of the two main tables within our load balancer. Whenever we're tracking our service, the services table contains all of the resources for services that's available. The key is the handle because that's going to be unique. And also for the communication that's coming in, we use .zw, and it's easier then to grab data from the services table because we just use .zw and the key. The address allocated, the address of that resource, the source itself, what people will be requesting. I've also thrown in a live example of the gateway handle and the sequence number that's currently being processed on that resource, including the update time. When was it received? When did anything change, in fact? If we look here simultaneously, let's imagine another user fired a request for the exact same resource, and we only have one resource, one service. Then the query is put into the service queue. And all that maintains is the gateway handle, the sequence number based on that gateway, and the source that's been requested. They'll be executed one after the other. The combination of gateway handle and sequence number will allow you to have track an exact query from a user. It's a unique combination. And also the load balancer will maintain just a list of all of the active gateway handles. Within this, it can let all of the gateways know if there's a new resource that's made available that they need to connect to. So, service registration. This is just a very simple example of what you could have in your RDB or within your HDB. We need some way of managing the connection, so we created a function called manage_con. It's protected evaluation to make sure that we don't mess up anything. And let's just imagine that we're hard coding the service name in this particular case, but we more than likely have it in the input command line parameters. And then we create the service details, which is a combination of the service name that we provided and the host and the port of the service that's running. And this is what gets sent to the load balancer. So on initiation, the service details will be sent to the load balancer, told to execute the register resource function, and it'll be added to all of the services that are available. Gateways will be informed of the new resource, and if there's anybody waiting on that particular service, then they'll be informed that they can use it. Handle process disconnect. Now this is a fairly simple version of what you might see in the service process. If there's a disconnect and it's the handle of our load balancer, LB, then we want to set our handle to 0. And then what we're going to do is start the timer. And next what we're going to see is that, apologies. The timer is going to attempt to reconnect to the load balancer. It'll keep on trying until the handle LB has been assigned. And then whenever it's done, it'll fire off its registrations again. And also set the timer to 0. We don't need to use the timer anymore. If we go back to here quickly, this is the event handler for whenever a connection closes from the gateway side. Now, the gateway, as we've talked about, has to handle a lot more connections. It has to handle connections from the services, has to handle connections from the load balancer, and it also has to handle connections to the user. So this makes it a little bit bulkier. We've got to have a lot of different triggers in our event. Whether or not we're updating the user handle in the query table to null, the user is gone. Whether or not we have to delete a resource from the resources table, that resource is no longer available. Whether we have to let users know if the service is disconnected while they were making a query. And if the load balancer has disconnected, well, if the load balancer is disconnected, then we can't actually request any service. So we're going to have to try to reconnect to that load balancer, but at the same time clear out our resources table. Unfortunately, in that situation, the gateway it won't be able to execute any of your requests. Your request can't be allocated anymore. And finally, we will set the timer that we see in the next slide to try to attempt to reconnect with the load balancer. And the reconnect function is very similar, whether it's a service or a load or a gateway. They'll both try to attempt that to continuously reconnect to the load balancer. So that is a rough overview of all of the components and what I was trying to achieve within the white paper. We had a bit of a look at the framework design, the concept of query tracking, why we want to even do this. Load balancing, whether it's service allocation or a simpler version like mserve.q, and process connectivity management. And if you really want to look into the code of what I achieved within the framework, then the Q for Gods edition is available on the First Derivatives website, along with a lot of different fantastic white papers, so I advise you to have a look. Thank you very much, guys.